In this video, we're going to be tackling a common modeling problem. It's going to be an objective function mixed with some constraint functions in order to maximize profit. So let's go ahead and read through the problem. A drug manufacturing company produces three types of drugs, A, B, and C. The company uses two types of ingredients, 1 and 2, of which 4,000 and 6,000 grams are available respectively. The ingredients requirements per unit of the three drugs are as follows. They're shown in the table. For example, requirements for drug A, it requires 20 of ingredient 1 and 50 of ingredient 2. The machine hour required for each unit of drug A is twice that of drug B and 3 times that of drug C. The entire machine hour available in the factory is enough to produce the equivalent of 1,500 units of drug A. A market survey indicates that a minimum demand for 3 drugs is 300, 400, and 250 units respectively. However, the ratio of the number of units produced must be equal to 2 to 1 to 3 respectively. So for this problem, they're asking us to assume that the profit per unit of drugs A, B, and C is $40 for A, $30 for B and per unit, and $60 for C. Formulate the problem as a linear programming model to determine the number of units of each product that will maximize the profit. Very common industrial engineering modeling problem. Here they specify that you are strictly asked to only formulate the problem. You are not asked to solve the problem. Indicate our decision variables, XA, XB, and XC, as the number of units to be produced of drugs A, B, and C respectively. And in our formulations, we should follow the given steps. The steps are given in the questions A, B, and C, so as you'll see as the question goes forward. So you will rarely be asked to solve these problems throughout the program. There are a few courses, not here though, of course. It's mainly about formulating the problem correctly and modeling it with the correct constraints based on the given criteria. And usually you use digital solvers like Cplex and other softwares to solve these types of problems as they get very complex and very time consuming. So let's get started. For A, we're asked to find the objective function, right? So if we have that our decision variables are XA, XB, and XC. And these are the units of each of the three drugs. So units of drugs A, B, and C. So we can write our objective function. Objective function as such. It's going to be a maximization of profit function, right? So we're looking to maximize profit. So our objective function is going to be max the following function. Z equals, so we have that you make $40 of profit per unit of drug A. So it's going to be 40 times XA plus, it was $30 of profit per unit of drug B plus $60 of profit per unit of drug C. it's quite simple. We have to optimize this maximization function in order to know how many units of each of the three drugs we should make in order to maximize our profit. In question B, it asks us to write the constraint functions or formulas for the raw material usage. So here we use the table, which shows us how much of each of the two ingredients, 1 and 2, is used in each of the three drugs A, B, and C per unit. We also use the maximum available quantity of ingredients 1 and 2 given in the problem. So for example, in drug A, the amount of ingredient 1 used is 20 grams per unit. For example, I'm just putting metrics on these questions. I don't believe they're given it in grams. I'm not sure either way. Let's say 20 grams per unit. The metrics, the units don't really matter that much. And in B, the amount of ingredient 1 used, according to the table, is 33 grams per unit. In C, it's 50 grams per unit, right? So the number of units produced and the maximum amount of ingredients 1 available can be correlated by an inequality. So if you only have maximum, as stated in the question, 4,000 grams available of ingredient 1, that means that the sum of all of the ingredient 1 used in all three units, all three drugs, is going to have to be smaller or equal to 4,000. So let's go ahead and start here. So constraints for raw material usage. So our first constraint is going to take care of the usage of ingredient 1. So if the whole thing has to be smaller or equal to 4,000, because that's the maximum amount of ingredient 1 that we have. So if unit 1 per unit, drug A per unit requires 20 grams per unit, it's going to be 20 XA, right? So the number of units of drug A times the required amount of ingredient 1 is going to give us a total amount of ingredient 1 used for drug A. But we also have to do the same for drug B and drug C. For drug B, from the table, we see that it's 33 per unit. And for drug C, it is 50. So we can see how the number of units produced and the amount of ingredient 1 available, 4,000 grams, can be correlated through this inequality. The less than or equal keeps it below 4,000 so that we don't produce more units than we actually have ingredients for. We now have to do the same thing for ingredient 2. Now the coefficients are going to change. So we have 50 XA plus 20 grams per unit of XB plus 60 grams per unit of XC. And the maximum amount of ingredient 2 that we can use for across all three drugs A, B, and C is going to be 6,000. And those are the constraints for raw material usage. Above, I've left the objective function from the previous question so that you can kind of have all of the things put together. I forgot to mention that at any point, feel free to pause and take a look at the table with all the values, or to reread the question. All right. In question C, we're asked to write constraints relative to the machine hours. So constraints regarding the time it takes to produce these units, right? So because you're actually not giving any time or amount of time, like any direct time it takes to make any of the, or produce any of the drugs A, B, and C, this can be a little bit confusing or maybe intimidating of the question. It's not that hard. So what we are given is that if using the entire workday to only produce drug A, we can make 1,500 units of only drug A, right? And since the time required for a unit of drug A is twice that of drug B and 3 times that of drug C, we can deduce that in the time it takes to make 1 unit of drug A, we can make 2 units of drug B and 3 units of drug C. So it's kind of, we're using amount of units, relative amounts of units produced instead of actual time, as in seconds and minutes per unit. So let's go ahead and tackle this part. So for 1 unit of drug A, 1 times drug A, we get 2 units of drug B. Also, for 1 unit of drug A, we get 3 units of drug C. Now, if we're only making drug A, we can, for the entire day, the entire available time, whatever that is, 2, 3, 24 hours, we are given that we can make at most 1,500 units of that drug A. But we're not only making drug A, so we have to represent drug A as the corresponding summation of all possible drugs that could be made at the same time. So we have drug A, this is our actual constraint, plus its equivalent in drug B, right? So for 1 drug A, we have 2 drug B units, plus it's the equivalent of drug A in drug C, which is 3, times units of drug C, has to be smaller or equal to the maximum amount of drug A that we can produce in the entire time allocated at 1,500. And that's our machine hour constraint. So for question D, we're asked to write demand constraints, right? There's a demand specified in the question. Constraints. So our demand constraints, they can be defined as 3 separate inequalities using the minimum demand values given in the questions. This is quite straightforward. So we are forecasting a demand of at least 300 units of drug A, 400 units of drug B, and 250 units of drug C. So we want to make at least, the reason it's bigger or equal is we want to make at least 300 of drug A, 400 of drug B, and 250 units of drug C in order to meet demand and not miss out on any profit. For question E, which we could put over here, we're asked to write relative production amount constraints. This can be a little bit confusing, but we'll tackle it together. So, relative production amounts. So constraints on relative production amounts can be defined as three separate inequalities, and we can just use the ratios given in the problem directly as coefficients in front of each of the decision variables, xa, xb, and xc. So we were given in the question that the relative production amounts for drugs A, B, and C are respectively 2 to 1 to 3. So those are our coefficients in front of the decision variables xa, xb, and xc. So here we go. So it's 2 to 1 to 3, which means that 2 times xa has to be equal to 1 times xb. It also means that 2 times xa has to be equal to 3 times xc, and that xb, 1 times xb, has to be equal to 3 times xc. So those are our relative production amounts constraints. Finally, we're asked to add some non-negativity constraints, as you do with all optimization models, or most, until for the early courses of industrial engineering, until you get to some more complex stuff, in order to avoid x, a, b, and c taking on negative values, as we cannot have negative amounts of units, right? And these are obviously very simple. It's question F, non-negativity. And these will just be x1, xa, xb, and xc, our three decision variables, must all be bigger or equal to 0. And here's the entire modeling problem.